right back into section 1 of chapter 7. We're going to finish it up. And we're in the process of going over how polar coordinates can be used to graph and how to convert between polar coordinates and rectangular coordinates. We did a couple of examples in the last video where we took polar coordinates and we converted them into rectangular. We'll do one the other way around here. We have rectangular coordinates, the ordered pair 2, -3, and we're going to convert these to polar coordinates. Now, I didn't bring my calculator with me, so I'm going to have to most likely leave my answer in terms of an inverse tangent here. But the first things first, we want r theta. Remember, polar coordinates are r, and I use a semicolon theta. So r can be found by going through this process. Now, remember, 2, -3 is in the fourth quadrant, right? 2 over 3 down, you're in the fourth quadrant. So, I keep track of that because I want to make sure that my polar distance and my polar angle match up and put me in to the fourth quadrant. So first things first, r is equal to plus or minus the square root of 2 squared plus -3 squared, which is the plus or minus, I guess I should write that, plus or minus, of the square root of 13. So let's find my angle. My angle can be found by using theta is equal to the inverse tangent of, let's see, -3 over 2. Now, the inverse tangent, remember, is going to give me an angle that's in between -90 and 90, or between -pi/2 and pi/2, not inclusive, because that's its range. So since this is a negative value, I'm going to get a fourth quadrant angle. And I said I was in the fourth quadrant, so I want the positive value here, because that's going to put me in the fourth quadrant. So my r theta here would be the square root of 13, and then I don't know what this is right off the top of my head, but it would be the inverse tan of -3/2. It's probably, let's see, -3/2. It's probably pretty close to about 55 to 60 degrees if I had to take a guess. -55 to 60 degrees. But without my calculator here, I can't come up with a decent approximation, so I'll leave this exact value. Now, we are converting coordinates from polar to rectangular, rectangular to polar. We can do the same thing with the equations, because we're used to working with rectangular equations. Here's a couple of examples of rectangular equations. I have a horizontal line and I have a parabola. We may want to see if we can convert this into a polar equation. Now, with a rectangular equation, the variables are x and y. With a polar equation, the variables are r and theta. And typically we solve for y when we have a rectangular equation, and we have y all by itself on one side if we can, conveniently. With a polar equation, we'd like to have r by itself on one side in terms of theta. And then we'll try it the other way around here. But first things first, why would we even bother with this? These are very simple looking equations. Well, it's because when graphs have simple equations, you know, it's probably best to stay in rectangular, okay? If these equations are simple looking, let's leave them this way. But some graphs have equations that are very complicated in rectangular form and are more easily written in polar form, okay? So that's why we want to be able to do both. Now, what kinds of graphs have simpler equations in polar forms? Well, graphs of things that we haven't really discussed, but have loops in them, like what we call a 3 or 4 or 5 petal rose, or a cardioid. And I know that doesn't make a lot of sense to you right now. It will, but those are the types of graphs that are more easily written down. The equations are more easily written down in terms of r and theta as compared to x and y. So we're going to just practice converting back and forth here just to make sure that we know how to do it. We're going to use the same conversions right here. We're going to use the same conversion forms as we did with the coordinates. So over here I have y equals -3. Well, according to my polar form here, to go from rectangular to polar here, I'm going to make the adjustment here, and I'm going to replace y with r sine theta, because that's what y is equal to in polar form. And what is this? I said before, we want to solve for r. We'd like to, just like the y is typically written by itself, on one side. We want to do the same thing in polar form with r. So I'm going to divide both sides by the sine of theta. And I have r equals -3 over the sine of theta, or -3 cosecant theta. And that's it. It's about as simple as you can get it. Now, they're not that much different as far as how, you know, complicated they are, but they represent the same horizontal line. This in rectangular form, this in polar form. Over here, I'm going to use these guys here. I'm going to plug in over to here, and I'm going to start out with y was r sine theta, and x is r cosine theta. But that x is squared, so I have r sine theta is equal to r squared cosine squared theta. Now, I'm going to try to solve for r, but you can see r is written twice, and in fact it's r to the second power on the right. Since they both have a factor of r here, I'm going to divide both sides by r. And I have the sine of theta is equal to r cosine squared theta. Now I'm going to divide both sides by cosine squared theta. I'm kind of running out of space here, so I'm going to go ahead and write r equals the sine of theta divided by cosine squared theta. Now there's nothing really all that wrong with it written in this form, but you know, just to avoid the fraction, I'm going to think of cosine squared as cosine times cosine, sine over cosine is tangent. I'm going to write this as r equals the tangent of theta, the secant of theta. About, you know, about the same as far as their degree of difficulty in writing it out. This is probably a more acceptable form. If you were checking answers from like odd problems and you looked in the back of the book, probably written this way as compared to being written this way. But notice I used the same substitutions that I was doing before when I was converting coordinates from rectangular to polar, polar to rectangular. Now here we have what we call polar equations. I have 4 examples here. Notice there's no x's and y's, they're all in terms of r's and thetas. We're going to write an equivalent equation using the rectangular coordinates, and we're going to try to identify the curve that this equation represents. So what I'm going to start off with here is I have r equals -3. Well, what's r? Well, let's go back to here. R is equal to plus or minus the square root of x squared, this is part A here, of x squared plus y squared. And that equals -3. Now, I'm going to be able to identify the curve that the equation represents. I can't really do it here. I'll square both sides. Let's get rid of the plus or minus, and let's get rid of the radical. I'm going to square both sides. And I get x squared plus y squared is equal to 9. Well, there we go. That guy I recognize. That's the equation of a circle. Center 0, 0, and radius 3. That one wasn't so bad. Let's go over to this one. Let's plug in for theta. What do we have? We have theta is equal to the inverse tangent of y over x. See if I have enough space here. Hopefully I can do all this. So in for theta, I'm going to plug inverse tangent of y over x, and that equals -pi over 4. Well, that's kind of awkward. There's no way right off the top of my head I can recognize that as any kind of an equation of, to represent what kind of curve it is. So I am going to have to get rid of that inverse tangent. And so to do that, I'm going to take the tangent of both sides. Because when you take the tangent of the inverse tangent, you're going to get right back to the original expression here. These are going to kind of practically cancel one another. I'm taking the tangent of both sides. So the tangent of the inverse tangent of y over x is y over x, and the tangent of -pi over 4 is -1. You can check your unit circle. Multiply both sides by x, I get y equals the opposite of x. Well, that's a line. Okay, y-intercept 0, 0. Slope is equal to -1. All right. See, I look at this. There's no way I think that this is a line. I look at this, there's no way I think that this is a circle. Until I make the change and put it back in terms of x and y, then I can identify it. Now, we did enough graphing in using polar equations, we'd be able to look at this and know right away, oh, this one's a circle, this one's a line. It kind of makes it wonder what this one's going to be. R equals 6 secant of theta. So let me see what I can do with this one here. R equals 6 secant theta. I'm thinking if I because secant is 1 over cosine. If I multiply both sides by cosine, R cosine theta equals, well, if I multiply this by cosine, let's see if I have enough space to write it all here. These are reciprocals, they're going to cancel out. I'm going to get R cosine theta is equal to 6. Well, R cosine theta, where's it at? Where's it at? Where's it at? There it is. That's equal to x. So this is x equals to 6. So this is a vertical line. And again, I look at that, I mean, I had no idea that this was going to be a vertical line. But once I make the conversion, I can see exactly what I'm dealing with in terms of rectangular coordinates. I'm much more familiar with rectangular coordinates. One to go. Now this one doesn't look all that much different than this one. I wonder if this is another kind of a line, maybe. So let's see what we have here. We have R equals 6, the sine of theta. Now I can't divide both sides or multiply both sides by the reciprocal there because R cosecant isn't up there, so I'm going to have to approach this in a slightly different manner. Maybe what I'll do here, and I'm going to probably be out of space, is I would like this to have an R. I'm going to multiply both sides by R, right here. So this gives me, I'm going to kind of move it over here, I'm going to have R squared is equal to R, oops, let's put the 6 in there, 6R sine theta. Okay, well, see, the reason I do that is because I know what this is. R sine theta, that's over there, that's the y. And R squared, well, here's R, plus or minus this, so R squared would get rid of the radical. So R squared is x squared plus y squared, and this would be 6 times y. Well, if I subtract 6y from both sides, I get x squared plus y squared minus 6y equals 0. If I add 9 to both sides and complete the square, I would get x squared plus, this is a perfect square trinomial, this would be y minus 3 quantity squared equals 9. Well, that's the equation of a circle. This is a circle. Center is 0, 3. Radius is 3. Now, in general, there are a couple of graphs that I did up here that you should look for, this type and this type. If you have R equals a number, it's going to be a circle, okay? And the radius of the circle is going to be whatever A is, or the absolute value of A. Because as you can see here, A was a negative number. If I have theta equals some angle, I don't know, alpha or something like that, that's going to be a line. It's going to go through the origin, just like this one went through the origin, and the slope is going to be the tangent of that angle. It's going to give you the slope of the line. So that's kind of a cool thing. So we're trying to get used to this by doing some practice problems because we're just, this is kind of new to us, and we need to make sure that we do enough practice so that we become familiar with some of the subtleties of the rectangular and the polar equations.